With multiple regression, you really want to come to the most appropriate model to fit your data or the most appropriate model to predict your outcome. This means you want enough variables to adequately predict your outcome variable, but you also want to keep it what's called what we say parsimonious. So that just simply means you want the model to be simple. So this last thing we're going to do today is what's called model reduction. And that's just removing variables that aren't actually adding predictive power to our model. And when you decide if you want to remove any variables from your model, you're not just going to look at whether it's a significant predictor. You want to consider the shared correlation between your variables as well as the standardized beta. So I'm going to scroll back up to our regression model output, and we can decide which variable or variables to remove from the overall final model. Now, innovative is a significant predictor, so we definitely want to keep that one. And it's also the most influential predictor in the full model. And hours spent building is a non-significant predictor. And in fact, it's very comfortably non-significant. The p-value is really far from 0.05. So we're not going to include that one in the final model. It had a non-significant simple regression, non-significant correlation, and it's also a non-significant predictor in this model. And it is also the weakest predictor at a standardized beta of 0.11. Now, research is a little bit trickier to decide if we want to keep it or remove it. Remember, we want a model that best fit the data. So we do want to include the appropriate number, the appropriate variables to predict judges' rating. In the simple regression, this variable was significant. And it does seem to have a bit higher of a standardized beta compared to build. And we should also consider the shared variability between research and build. The fact that they were highly correlated is probably influencing the strength of the beta coefficient in this model. So I would say that we should keep this predictor in the final model and just see what happens. Also, our p-value is pretty close to 0.05. So we might see that by removing build, removing that shared variability, this predictor becomes significant. Okay, so let's go ahead and fit this final model. The command here is simply regress, the DV ratings, and our two independent variables, research and innovative. And let's keep this comma beta here to get the standardized beta. So there are a number of things that you want to consider when doing model reduction. And the biggest one is looking at our R squared, comparing the R squared from the reduced model compared to the original model. So here we have an R squared of 0.55. So in the model with two predictors, we're predicting 55% of the variability in overall judge ratings. Let's compare that above to the three predictor model. Here, we're predicting 56% of the variability. So in the three predictor model, again, we're predicting 56% of the variability. And in the two predictor model, we're predicting about 55% of the variability. Now, of course, when you remove variables, your R squared will be a little bit smaller, but you want to consider the magnitude of change of R squared. In this case, we've only lost about 1% of the variability that we can account for by removing hours spent building. That means hours spent building really wasn't predicting unique variability in judges' ratings. In fact, it was only accounting for about 1% of unique variability in judge ratings. So, right off the bat, it looks like by removing build, we haven't lost very much, if any, predictive power. Okay, and the model itself is significant with an F of 13.02. So again, that's just saying that the model with two predictors is better than no model at all. And now by removing build, research is again a significant predictor of judge ratings. Okay, so the beta coefficient didn't change that much, but what this is saying is that when you remove some of that shared variability, it's freeing up research to be a significant predictor of judge ratings. And remember, this p-value is simply saying that 3.94 is significantly different from 0. Okay? Our innovation beta hasn't changed very much at all either, 6.83, and again, it's a significant predictor. And then finally, the standardized betas for each coefficient also hasn't changed too much. And of course, innovation is still the strongest predictor of overall judge ratings. All right, so now that you've done all of this work, you've used data from last year's science fair, you've gone through all of the process for model reduction. You have this final model that you think is a really good predictor of judge ratings. Now you can actually start to predict judge ratings in the future. So let's say you have a client come to you, a student who researched their topic for 10 hours and had an overall innovation score of 3. Remember, 3 out of 4. They come to you and ask, what can they expect for their overall judge ratings? To determine this, all we have to do is fill in the regression equation. So in this case, our predicted y will equal the intercept, which here it's negative 15.21, plus the beta for research, 3.95, 3.94, times hours spent researching, plus the beta for innovative, 6.83, times innovation. Okay, now all we have to do is fill in for x. So our predicted value for the student will equal, again, our beta or our intercept, $10, 6.83, times an innovation score of 3. Okay, and if you do this yourself on a calculator, you should come to the conclusion that our predicted judge rating is 44.73. You can either trust me or do it yourself. I recommend you doing it yourself. Right, so this is a pretty high judge score. I would tell the student that they can expect to do pretty well. They have a reasonable innovation score, and they did adequate research. But remember that innovation is the most important or the strongest predictor of ratings. So it might be the case that somebody with the highest innovation score will still beat out this project. All right, so the final step, step 8, is to actually interpret our results. So let's consider which model was best. You probably already have a sense of that based on what I've said, but let's still go ahead and compare each model. So the model with 3 predictors had was a significant model, and it accounted for 56.4% of the variability, but it only had it only had one significant predictor. So 1 out of 3 of our predictors was significant. After model reduction, the model with 2 predictors was still significant with an F of 13.02, and we only lost about 1% of explained variability. And now importantly, both of our predictors now, both hours spent researching and innovation, do significantly contribute to overall judge ratings. Okay, and that's because when we remove this circle here, when we remove the predictor build, we're freeing up all of this variability to predict judge ratings, to account for scores of judge ratings. So this model with two predictors would be considered the most parsimonious, but also the best in predicting judge ratings overall. All right, so that brings us to the end of this worksheet. If you do have additional questions, I encourage you to reach out to your tutor. I also recommend that you kind of test this all out on your own if you haven't already. Make sure that you can run these commands and interpret the output. And I believe this is going to be our last week with regression. So we're going to be switching gears and moving to t-test and ANOVA in the next few weeks. All right, and have a good week.